The principle of CPT symmetry dictates a strict rule for the universe. If you reverse a particle's charge, invert its parity, and reverse its time, the resulting antimatter must behave exactly identically to normal matter. The physical reality of the universe, however, tells a different story. Because matter and antimatter annihilate upon contact, a universe created with perfectly equal amounts of both should be entirely empty, filled with nothing but light. Instead, we live in a universe built exclusively of normal matter. At the CERN laboratory, the ALPHA experiment is actively testing this contradiction. It isolates and interrogates anti-hydrogen atoms using precise laser pulses to see if this theoretical symmetry actually holds up in physical reality. To understand why researchers are measuring these atoms down to the 10 billionth decimal place, we have to look backward, tracing the existence of antimatter back to its origins as a forced mathematical consequence in early quantum mechanics. Physicists identified antimatter as a mathematical paradox on a chalkboard, emerging when they first attempted to merge Einstein's relativity with the laws of quantum mechanics. In the early 20th century, theoretical physics hit a bottleneck. The Schrödinger equation successfully described the time evolution of quantum systems, but it only worked for slow-moving particles. It needed to be merged with Einstein's relativistic energy-momentum relation to account for particles moving near the speed of light. The first attempt placed momentum under a square root, which mathematically requires an infinite series of spatial derivatives. To remove this non-locality, physicists squared the operators, reorganizing the math into the Klein-Gordon equation. This introduced a second-order time derivative, which created a conflict with the core rules of quantum mechanics. A valid wave equation must produce a positive probability, but this formula could output a negative probability. Furthermore, solving this squared equation for energy yields both a positive and a negative solution, stating a particle could possess less than zero energy. By squaring the equation to fix the non-locality problem, physicists accidentally broke causality and birthed the concept of negative energy. Paul Dirac set out to engineer a completely new equation. His objective was to maintain a first-order time derivative to save the probability density while keeping the math local and linear in momentum. He constructed a linear Hamiltonian. To balance the equation, he introduced unknown mathematical components, the alpha and beta matrices. To satisfy the required anti-commutation relations, these components could not be simple numbers, but had to be even-dimensional matrices of at least 4 by 4. The physical consequence of this math was that the wave function itself could no longer be a simple one-component value. It had to be a 4-component object, called a spinor. When you calculate the properties of a 4-component spinor, it predicts particles with a half-integer spin. This matched the known behavior of electrons, establishing the mathematical architecture for all fermions. While Dirac fixed the probability problem, the trace of his new matrices still yielded eigenvalues of positive E and negative E. The negative energy paradox remained in the math. In 1932, cloud chamber experiments confirmed these negative energy mathematical results as physical entities, positrons. This left physics with a glaring paradox. How can a physical particle actually possess less than zero energy? Dirac initially proposed the C picture. He suggested that the vacuum of space is completely filled with negative energy electrons. When energy is added, an electron is promoted out of the C, leaving behind a physical hole that we observe as a positron. Because this model relies entirely on the Pauli exclusion principle to prevent normal electrons from falling into those negative states, it completely fails to explain the existence of antimatter for bosons, which do not obey this exclusion principle. A universal resolution arrived through the work of Richard Feynman and Ernst Stueckelberg, who applied a strict standard of causality to the mathematics. If a negative energy state propagates backward in time, the equations behave consistently with causality. Reversing that temporal trajectory mathematically requires reversing the charge, transforming an electron moving backward into a positively charged positron moving forward. This causality fix establishes the requirements for CPT symmetry. If you flip the charge, invert the spatial coordinates, and reverse the time, antimatter behaves identically to normal matter. That theoretical derivation brings us to the physical testing currently occurring at CERN. The ALPHA collaboration was established to test whether this exact mathematical symmetry holds up in the real world. The experimental constraints are severe. Physicists produce anti-hydrogen atoms and capture them inside a cryogenically cooled, vacuum-tight magnetic trap. If an anti-atom touches the chamber walls, it instantly annihilates. While suspended in the trap, the anti-hydrogen is subjected to spectroscopy. The team shines a highly precise laser beam into the chamber, tuned specifically to excite the atoms into a 1s-2s energy transition. Atoms only absorb light at very specific frequencies. By measuring the exact distribution of those absorbed frequencies, researchers map out a unique fingerprint for the anti-hydrogen atom. Because spectroscopic measurements are among the most precise in science, this is the perfect arena to test the Dirac and Feynman models. If the math is right, the structural fingerprint of anti-hydrogen must perfectly match normal hydrogen. In 2016, the International ALPHA team published their findings. The anti-hydrogen spectrum was entirely consistent with normal hydrogen, down to a relative precision of 2 parts in 10 billion. CPT symmetry holds up against the most stringent tests humanity can devise. The mathematical derivations of Dirac and Feynman are accurate. Yet, the contradiction remains. The math demands equal creation, and physical tests prove matter and antimatter behave identically. Yet the universe we inhabit is composed purely of normal matter. Because every test proves matter and antimatter are twins, the absence of antimatter from the observable universe remains a fundamental contradiction. The symmetry required by the math is perfect, yet the universe we inhabit is lopsided.